Today, we're going to break down the algorithm that powers, everything from the lightning-fast recommendations you get to the magic behind searching with an image. It's called HNSW, and it's pretty much the engine that makes the modern data world go round. So let's get right into how it all works.
So picture this. You've got 1 billion songs in your library. A user listens to one, and you need to recommend 10 similar ones, like right now. How in the world do you do that? I mean, checking every single song one by one? That would take forever. This is the exact massive problem HNSW was born to solve.
And yeah, the solution isn't just throwing more computers at it. It's about creating a really clever roadmap of your data so you don't have to check every single thing. It's all about having a way smarter strategy from the get-go.
Okay, so the absolute best way to wrap your head around this is to think of HNSW as a super intelligent GPS for your data. Right? Imagine trying to find one specific house in a huge city by just driving down every single street. You'd be there forever. Well, HNSW is like having a GPS that knows all the interstates, all the main roads, and all the shortcuts to get you there in minutes, not days.
And that's what HNSW stands for, Hierarchical Navigable Small World. Now that name sounds super complicated, I know, but it's actually a perfect description. It builds these multiple layers of connections, a hierarchy, that act like express lanes, letting you just jump across huge, totally irrelevant parts of your data.
So how does this whole search journey actually work? Well, it all starts at the very top layer, on what you can think of as the interstate highway. This layer is really sparse. It only connects a few major points. But this is where you make those huge cross-country jumps, instantly going from, say, the rock music part of your data all the way over to the classical region in a single hop. Boom.
All right, once you're in the right state, it's time to get off the highway and onto the main roads. You drop down to the next layer in the hierarchy. This level is a lot denser, it's got more points, shorter connections. This is where you go from that high-level city view down to the right specific neighborhood. You're zeroing in now.
And finally, you take that last exit ramp down to the local streets. This is the very bottom layer, and it's the only one that has every single data point in it. But here's the genius part. Because those higher layers already dropped you off in the perfect neighborhood, you only have to check a handful of your immediate neighbors to find the closest match.
And that right there, that's the secret sauce, this whole coarse-to-fine strategy. It's all about making a few smart, high-level decisions first so you don't get bogged down in the tiny details later. By starting super broad and then getting more and more specific, HNSW just completely avoids looking at the vast majority of the data. It's brilliant.
So this GPS analogy is great, but what's actually going on under the hood? Let's peel back the layers for a second and look at the technical blueprint of what's happening.
Now, what's really cool is how this technical view maps perfectly to our analogy. The hierarchical layers are our different road systems. Those long-range links at the top, those are our interstate highways. As we go down, the layers get denser until we hit the short-range links, our local streets, at the very bottom. And how do some points get to be on those express layers? Well, it's all done with probability, basically ensuring you have a perfect number of on-ramps all over your data map.
We keep saying HNSW is fast, but just how fast are we talking? Well, the answer is kinda ridiculous, actually. Let's look at the math that makes this all possible.
This little expression, O log n, is the key to its incredible power. What it means is that even if your data grows 1,000 times bigger, the search time only goes up by a tiny amount. It's like adding 1,000 new houses to a city, but the time it takes to find any single one only increases by a few seconds. It's like the problem barely gets harder no matter how much data you throw at it.
And check this out. This is what that actually means in the real world. To find the closest item in a set of 1 billion, a simple search has to do 1 billion checks. HNSW, it can find a really good answer in about 30. That's the difference between a task that would take a computer years and one that's over before you can blink. That's not just an improvement, it's a total revolution.
But all this power doesn't just happen. It comes with a few knobs and dials you need to turn. HNSW isn't a one-size-fits-all thing. So let's talk about how you actually tune it to get that perfect balance of speed, accuracy, and memory for what you need.
This is the key question for anyone actually using HNSW. Do you need perfect, 100% accuracy, or is a blazing fast, good enough answer actually better for your use case? Are you working with tons of memory, or are you on a tight budget? The way you answer that completely changes how you tune this engine.
Think of it like tuning a race car, okay? M is like the width of your tires. Wider tires give you more grip and better navigation, but they also use up more resources. efConstruction is how much time you spend building the car. You spend more time, you get a higher quality car, or in our case, a better map, but you have to wait longer to race. And efSearch is how aggressively you take the corners. Pushing it gets you more accurate results, but it takes a little more time on each lap.
Now you see this term dimensionality here. Don't let that scare you. All it means is how many features you're using to describe something. A point on a map has 2 dimensions, right? Latitude and longitude. But a modern AI embedding that captures the meaning of an image, well, that can have thousands of dimensions. So for that kind of complex, high-dimensional data, you just need a more detailed road network, a higher M to navigate it well. And of course, if you need the absolute highest accuracy, you crank M up even more, assuming you've got the memory to handle it.
So we've gone on a whole journey here, from highways all the way to logarithmic speed. But if you remember just one thing from all of this, please make it this. At the end of the day, HNSW is just a super smart transportation system for your data. It builds express lanes to let you skip all the traffic, and it turns what should be an impossibly long search into a really quick trip. But there is a fascinating trade-off at the heart of all this incredible speed. HNSW is what's known as an approximate algorithm. It basically trades a tiny chance of missing the single absolute best match for a massive, game-changing gain in speed.
And that leaves us with a pretty big question, doesn't it? In a world that is just drowning in data, is the constant chase for perfection actually holding us back? HNSW suggests that maybe, just maybe, a good enough answer right now is infinitely more valuable than a perfect answer that comes way too late.
So, if this explainer helped you navigate the complex world of HNSW and you feel like you've got a better roadmap now, do me a favor and hit that like button. And subscribe for more deep dives into the tech that's really shaping our world. Thanks for joining me on this one.